Yes, Muhammad, you can start.
Okay, Bismillah. Welcome everybody. My name is Muhammad Hijazi. I'm a master student from Antalya University. Today, in my presentation, I want to talk about my thesis, which is entitled Signal Space Diversity and Convolutional Neural Network Based Equalizer for Improving the Reliability Performance of Orthogonal Frequency Division Multiplexing with Subcarrier Power Modulation. This is the points that I want to talk about. I will speak about small introduction and what is OFDM-SPM and signal space diversity, maximal ratio combining, and the convolutional neural networks. And I will show my results after I have made my simulation. Before I talk about signal space diversity and CNN, let's have a look at the state of the art at 5G technology and related other areas. Usually, what motivates us to develop a new technology is basically the emergence of new applications. These applications give us some requirements that we need to meet and cope up with. As you know, in 5G, we have three basic use cases: enhanced mobile broadband communication, massive machine type communication, and ultra reliable low latency communication. So basically, the first class of these services need extremely high spectral efficiency to provide high data services for application like virtual reality and real video communication system. So for that reason, we need a new technique and a new method, new ways in order to achieve that demand. So one of the best solutions is to increase the spectral efficiency in efficient manner by using more intelligent techniques. OFDM that has been in Wi-Fi, 3G, and 4G have been used, but the problem with OFDM that it has some issues related to being about peak to average power ratio and out of band emission, and this can reduce its spectral efficiency. To improve spectral efficiency, furthermore, a new technique has been introduced that adds a new dimension to increase the amount of data rate that we can send in wireless channels. This technique is known as orthogonal frequency division multiplexing with subcarrier power modulation, OFDM-SPM. So, what is OFDM-SPM? It's a technique that sends additional data bits by varying the power of each subcarrier in OFDM symbol. So each carrier sends the QPSK or QAM symbol, and the variation of each subcarrier carries additional data that can send for your transmitter. So it's double the spectral efficiency and can save half of the power that is needed to transmit data. And this is, you know, it's important in Internet of Things. It also makes low latency that's more efficient in our communication. So in this figure, here is an example of OFDM-SPM paired with QPSK modulation. In the original case, we have OFDM works with like subcarrier back to each other, and each subcarrier carries data symbol. So for example, in a quadrature component or an in-phase component, when we carry these 6 data samples, we carry them only in half bandwidth and also half the power. So in OFDM-SPM, we send the same amount of data using half of the power, half of the latency, and half of complexity. But despite all the merits that have been achieved from OFDM-SPM, it was found that the additional data stream conveyed by subcarrier's power has a higher bit error rate performance compared to the data stream conveyed by conventional modulation schemes. In order to overcome this shortfall, I have used 2 different methods. Every method depends on a known technique by adding these techniques and merging it with OFDM-SPM. Here you see in this figure that OFDM using SPM, the QPSK, it appears in the constellations just like 16 qua. So, what is my contribution? My contribution is to design and build a system model that can improve the bit error rate performance for the ready OFDM-SPM by using these two methods. First one, by using signal space diversity, and the second method is by using one of the deep learning technique, and I choose convolutional neural network, CNN. Let us begin with method 1. So what is SSD? It is a technique that improves the performance over feeding channels, since there is no need for using extra bandwidth or extra power. The basic concept of SSD is the multidimensional signal constellation used and the component of each signal constellation point that is transmitted over independent feeding channels. So the independence of the feeding channels can easily be accomplished by interleaving. Right now, we have two strategies for using SSD. The first one is rotation. Here, let us begin with the rotated constellation. Here's in this figure. I made a rotation for this constellation, which is in phase and quarter component for the symbols or the subcarrier. And this ensures that no two symbols in the signal constellation has identical in phase and in quarter component. And this will make interference intersymbol and increase the potential of the bit error. So by rotation, by making a rotation, our goal is to maximize the minimum product distance of the rotated constellations, as we can see in this figure. Here, when there is a fading in the channel due to multipath, we see that the minimum product distance is reduced between any 2 points. But in case of rotation, the distance is still higher, and that will be against fading. But this is inadequate because we need to make the second step. The second step is the interleaving. In order to destroy the correlation between the I component and the in-phase component, which will make I and Q channels independent, therefore, the received data can be recovered. Even though one of the components suffers from deep fading, still the other component will come stable. In other words, I want to explain this by this figure. We make a delay to the quarter component in the subcarrier, as in the interleaving process, the real part will bypass and the imaginary part is interleaved in order to avoid the worst channel condition, where both parts experience deep fading simultaneously. So here's an examples for SSD. I have 3 slides. We will see an examples for SSD conditions. First example, first one, only one condition has been applied, which is the interleaving. You will see that the rotation angle equal to 0. And when I make interleaving, there was no change in the bit error performance. But when I made a rotation angle of 15 degrees and make a coordinate interleaving, there was an improvement in the bit error rate performance. Then I increased the rotation angle to 30 degrees, and also the bit error rate improved better and better. Right now, this is the system model. I will go to the structure of my proposed system. At the transmitter side, the system does not introduce too much complexity. At that, we just split our bits to two parts or two streams. The first one, we take it and modulate it conventionally using a QPSK. And in this case, a group of 2 bits is mapped into a complex modulation symbol. The other streams of bits, we change the power of the subcarrier. If it is 0, low power, and if it is 1, so it is high power. Then a modulator constellation is rotated anti-clockwise by applying some rotation angle to ensure that no two symbols in the signal constellation has identical in phase and in quadrature. And this will make interference intersymbol, just like I said before, and increase the potential of the bit error rate. After that, we will go to interleaver. So without interleaving, I and the Q components experience the same fate. Also, there were 2 orthogonal channels available, but they experienced the same fate. So no diversity gain is achieved. So in the subsequent analysis, we will consider a scenario where the I and the Q channels experience a different fates. After that, we take the output to the conventional OFDM system, contains IFFT, convert from signal frequency domain to time domain, then adding cycle prefix, and converting from digital to analog, then to antenna, and then to the channel. Then we will go to the receiver system model. Here we know that here we know that the signals that are coming from the transmitter will have many problems due to the fading channel that carries it due to multipath fading channels. So in other words, we have Rayleigh fading effects and also a normal AWG and additive white Gaussian noise. So after receiving a signal from receiver antenna, the analog to digital converters convert signal from analog to digital. Then the cycle prefix will removed and go to the FFT and return back to the time domain, from time domain to frequency domain. And also the subcarrier go to the de-interleaver, as every subcarrier have its original components, which are in phase and quadrature components. So bits that have been transmitted by a power subcarrier allocator will be recovered, and for the other constellation point, which was modulated by QPSK, it will be derotated so that all incoming bits will received after converted from parallel to serial, and then we have our data received. I want to, before showing my results, I want to speak a little about maximum combining ratio. And I will also compare my results that came from SSD with the MRC and also the conventional OFDM model. For the MRC system model, I used 2 antennas to receive the same signals from the 2 channels and combined these signals using their weights in the MRC combiner. Note that this will happen after remove the cycle prefix and the FFT process. So here at the receiver side, because the transmitter side will be the same, I used 2 antennas and to receive the same signals, and also for maximum ratio combining. But first, I want to talk small about maximum ratio combining. The rationale is that some channels are more reliable than others. So if I want to explain the MRC, something like if we listen to, if we have multiple individuals speaking, so if you hear something from multiple individuals, you probably will not weight each person equally, because you know who is more reliable compared to others. This is the principle of MRC. To prove my idea and show my, I will show my results after performing simulation analysis. I came up with these following results. Here, as you can see here in this figure, we note that when we use SSD to the conventional OFDM-SPM, we achieve or save 18 dB in the SNR. So, for example, the bit error rate at 10 dB, for example, in the normal OFDM or OFDM-SPM is 10 to minus 1. But in our case, when we use signal space diversity, we will get 10 to minus 2. And that's considered a significant improvement. And for the throughput here, we got the same throughput after 10 dB, or from 0 to 10, we have a better throughput. And for the case of power save mode, just like optimized power policy, there are poor performance for bit error rate for OFDM-SPM comparing to the normal OFDM. But on the contrary, with signal space diversity, the performance increase, and it's better than the normal OFDM. Here's also for the throughput, the same results. And when I use also the maximum ratio combining from the figure that I got it from my simulation, you will see that MRC does a small improvement for bit error rate comparing to OFDM-SPM, and also with the cost of the complexity. And at the end of the day, SSD or signal space diversity proved that it made better results. Here, note that the curve in yellow color that's related to the average OFDM SPM using SSD, and the non-continuous blue color that is related to the average OFDM SPM using MRC. You will see that to achieve 10 to minus 2 bit error rate, we need 22 dB in the signal to noise ratio. But at case of using signal space diversity, we need only around 11 dB to get the same bit error rate. Also, this is the result for throughput between OFDM-SPM in a non-optimized power, and also using maximum ratio combining and using this signal space diversity. Okay, right now I will go to my second method, which is using the neural networks or the convolutional neural networks. Neural networks were initially designed around the concept of how our brain's neuron works. So the CNN can adapt the weights such that they extract different features from the input images. So maybe, for example, one of the feature maps may extract edges and another one may extract circular shapes. Here is, first of all, I wanted to speak about the objective of my idea. The online network will be used after training the real transmission data to predict the OFDM-SPM symbols that have errors due to multipath fading. Then it will be recovered so that the bit error rate will be reduced. So proposed convolutional neural network equalizer is trained with an offline and end-to-end manner. Here's a friendly example about a CNN. I take it from image processing to make the explanation more easier. If we assume that there are two symbols, one for X and one for O, here X is not the same every time. Also O. Maybe it may be shifted or rotated, or it can be bigger or smaller, and this is due to noise or multipath fading in our case. So here there is a noise and fading in the channel. You see that there's a distortion in the X symbol. Here's we detect the feature maps. For example, the left one. In the convolutional layer, I tried every possible match. I repeated this with other features. So one image, or I can speak about OFDM-SPM symbol, becomes a stack of filtered OFDM-SPM symbols. Then here we will go to the pooling layer, which causes the simple stack to shrink. And after this, after pooling layer, so a stack of OFDM samples become a small stack of OFDM-SPM samples. And here the fully connected layer, which compiles the data extracted by previous layer to form the final output. And here vote depends on how much is the value that predicts the OFDM symbol. This examples is only to show how I apply OFDM samples in CNN methods. So the transmitter design for OFDM sample will still the same. I only here make a small amendment for the receiver design. CNN Equalizer block will be applied after the process of conventional OFDM, including the removal of CP and applying FFT. So the output of the CNN Equalizer, which is the in-phase and quadrature component, so that the bits that are transmitted by the subcarrier power allocator are recovered, and other constellating points which were modulated by QPSK will be derotated, so that all incoming bits will be received. So this is the equalizer model and the dimensions I have used in my CNN equalizer. Here's the input layer that symbols 50 parameters, and the convolution layer, activation function, and max pool layer, the fully connected layer, and the soft max layer, and finally the classification layer. So the proposed design for CNN-based equalizer, the input complex data symbols are reshaped into two separated channels. Each represents real and imaginary part to maintain the spatial disposition. Then for the convolution layer, that is the first layer in CNN, it is comprising of the 16 filters. Each of them has a size of 3 by 3. And applying clipped rectifier linear unit activation function to generate the output of the CNN layer. Then we will go to the max pool layer. A max pooling layer is applied to downsample the output of the convolution layer. And this layer operates by dividing the input into rectangular pooling regions and combining the maximum of each region. I implemented the pool size of 2 by 2 along with the step size of 2 by 2, I mean straight of 2. After that, for the fully connected layer, in CNN, the convolutional and max pool layers are generally followed by one or more fully connected layers. So all neurons in fully connected layer connect to all the neurons in the previous layer. The layer combines all the local information and features learned by the previous layers. After that, I put the softmax layers, which have softmax function, and the advantage of softmax is to limit the output of the function into the range from 0 to 1. And finally, we will go to the classification layer. It follows the softmax layer and applying the CNN and received our data. So this is the summary, the convolution layer and the Maximal layer, the fully connected layer, softmax layer, and finally the classification layer. Here, if I want to show my results, we can see here in this figure, after making the simulation, I analyzed again of around 5 to 10 dB SNR region. There is a significant improvement in bit error rate as shown. Also, the bit error rate becomes exceptional at the high SNR. About 4 dB SNR again is achieved at low SNR. But the obvious improvement, just like you see here, will start from the value of 8 dB in the signal-to-noise ratio. For the throughput, also for the throughput, it almost became double than the conventional model. Hence, the power of implementing the CNN in the receiver can be observed, and this gain in performance is at the cost of implementation complexity and additional time taking for the training of CNN. And this is one small disadvantages in the CNN. Finally, I want to speak about the conclusion. Mention the conclusion. What I conclude. We conclude that when we integrate signal space diversity to OFDM-SPM-QPSK, the effect of constellation rotation is only marginal, and the improvement in bit error rate is mainly due to the interleaving. Also, OFDM-SPM-QPSK using signal space diversity, it provides a considerable improvement in bit error rate and throughput over the traditional OFDM-SPM-QPSK, and also OFDM-SPM-QPSK using a maximum ratio combining. For the CNN equalization scheme, I think it is a suitable solution, even knowing that it is abolishes the need of channel estimation, interpolation, and element-wise division. But also, despite there is a considerable improvement in bit error rate and throughput, there is and disadvantages because it requires additional time and it will be required for training. The time of training, it takes a long time for making the simulation. And I think this is the final things of my thesis. This is the reference that I have used and searched about. Also, these references also. And thank you for your attention and for your patience.